So let's check this one out. We say that we've got an astronaut holds a rock 100 meters above the surface of planet X. The rock is then thrown upward with a speed of 15 meters per second as shown in the figure. The rock reaches the ground 10 seconds after it is thrown. The atmosphere of planet X has a negligible, that means ignorable, effect on the rock when it is in free fall. So basically the rock's in free fall. So it says determine the acceleration due to gravity of the rock when it is on planet X. All right, that's down here. So find the gravity on planet X. So I'm going to think about what information they've given me and start to write that down. I know the clearest thing that they've told me is that the initial velocity is 15 meters per second. I'm going to stick with the convention that up is positive and down is negative. We know that the time of this problem is 10 seconds, like that. And we know that the displacement in the end, I'm going to write the delta y is equal to negative 100 meters. You could also write it like this, at the final position, if we call this the origin, then we could just say that the y is negative 100 meters, basically the same thing. So, and we're looking for the acceleration. So what equation mentions initial velocity, time, displacement, and acceleration all at once? And it is the third one. So the third one looks like this. Y equals y0 plus v0t plus 1/2 at squared. But we're just going to call the origin 0. In fact, I pretty much always do that. So let's start to plug in. We know the final position is negative 100 meters. We know the initial velocity is 15. We know the time of the problem is 10. And we're going to look for the acceleration. And this is time is 10 squared, also gets plugged in there. So this will be 150, and you'll subtract it to the other side there. So 15 times 10 is 150. Subtract to the other side, you get negative 250 is equal to 1/2 times a. I'm going to go ahead and square the 10, so you get 100. 1/2 times 100 is 50, so negative 250 is equal to a times 50, and then divide each side by 50 to solve for a. So a is equal to 250 divided by 50 is negative 5 meters per second squared there. So basically half of what it is on Earth. The next question says, how does the speed of the rock when it reaches the ground, Vd, compare to the speed of the rock when it is thrown upwards, Vu? So here's the thing, if you throw it up at 15 meters per second, the path as it goes upwards, it will lose all its speed till it gets to the peak, and then it will start to come back down. By the time it gets back down to the same level that you let it go, it's going to be going negative 15 meters per second. That's right here. So it's already going negative 15 meters per second, so it's going to continue to pick up speed as it heads down there. So notice an important but subtle point is they do say how does the speed, so that means we don't care about the direction. So if it was velocity, you might get tangled up in the positive or negatives, but speed just means the number. So when we get over here, it turns out that the V down is greater than the V up, and we explain that, and I won't write it all out, but you heard me explain it on the front. It will get to 15 meters per second again on the way back down as it reaches the level of the cliff, and then continue to gain speed like that. So last part here says a student wants to know how the motion of the rock would be different if it was thrown upwards at 15 meters per second from a height of 100 meters above Earth's surface. So that's the difference there. In a clear, coherent paragraph length response that may also contain figures and or equations, explain how the motion of the rock on Earth will be different from its motion on the planet X in terms of its maximum height above the ground. So there's several things they want you to each here. What happens to its maximum height above the ground, the speed at which it reaches the ground, so this one right here, a second thing, and the time is which it is free fall, and the acceleration due to gravity. So you have to mention in this case here 1, 2, 3, 4 different things. So I'm not actually going to write it all out because that will be too slow, but this is a type of problem that you'll encounter where you want a paragraph. So you do want to write it, don't just put equations, you're not solving something, but you want to write it out as if almost like you're writing a little story here. So the clearest thing is, if I I mean, you want to write full sentences, but that the acceleration is going to be half of what it was, or it's going to be twice, what it was on planet X. So the acceleration now is 10 meters per second squared as opposed to 5 meters per second squared, both of those negatives. It says, remember that you can use equations to talk about it. So for example, you can bring this one back up here, initial y velocity times time plus 1/2 at squared. If the acceleration is greater, the overall trip is going to take less time to get to the peak, speed you up faster on the way back down. So the overall time in which it is in free fall should be less. And then the other thing that they would want you to say here is the maximum height it reaches above the ground. You could sort of use this to solve that, because the final velocity, actually we did this in class, v squared equals v0 squared plus 2 times a times delta y. So we solved this for the maximum height, because at the peak there is no final velocity, that will be 0. So I'll subtract this v0 to the other side, and I'll divide by the acceleration. So if we have twice the acceleration on Earth, we will only get to half the height that we had before. Let me read you the actual released official answer that they have. They say that the acceleration due to gravity for the rock is greater on Earth than planet X. Since the acceleration due to gravity is greater on Earth, the time it takes for the rock to reach its maximum height is less on Earth than on planet X. Therefore, the maximum distance above the ground the rock attains is less on Earth than on planet X. This also means that the total time that the rock is in free fall is less on planet Earth than planet X. When the rock is at the position 100 meters above the Earth's surface of Earth and planet X as it falls towards the ground, they say that you can use this equation right here to show that for the same height above the ground and for the same initial velocity of 15 meters per second downward for the rock will reach a ground with a greater speed on Earth than it does on planet X.